Anyway, okay. So I'm babbling too much. So review what we did last time. So I just mentioned we have the delta function potential, which is, well, the potential is, again, I forget this h bar over 2f, which was just done for convenience. This, I think, I can't recall if delta, Joyce does, I can't recall if delta functions have units or not. So I think you have this gamma to make it positive or negative and give it magnitude, give it units, sorry. Okay, and then what you found was kind of interesting about that one is, for one, it's an interesting exercise, right? So let's just get our math skills up. It's kind of worth doing just for that. Actually, on your next homework, I have some questions that are just purely about getting you more comfortable with taking derivatives of e to the x. It's entirely why I'm making you do that. You'll see on the next homework. So there's just the pure math aspect of this. What's also kind of interesting is you may have noticed that you did not use smooth and continuous. I guess it was continuous, but you did not use smooth. You did not use the smooth boundary condition. You actually used the Schrodinger equation to solve it, which again has to tell you is actually rare. Rare to actually use the Schrodinger equation to solve the Schrodinger equation. But in this case, you did. You basically did that in lieu of the smooth condition that the derivatives are equal. A delta function discontinuity actually breaks that. That actually breaks the smooth condition. That's also why your homework looks the way it does. Now, heads up on that. I know that it's like dogma that wave functions are always smooth and continuous. It's not true in this case. However, delta function potentials don't exist. Infinitely narrow and infinitely high, that's unreal. So again, so you've seen the math exercise of this kick in. If I plot the reflectance transmission as a function of E over gamma, see this behavior, so that would be reflection, sorry, that would be transmission because it goes up. And of course the reflection is that tick mark wasn't perfect, it would be crazy. There we go. So there you go. And now you're seeing transmission being more than 0, even if you don't have enough energy to go over the barrier, which that's just what quantum does. Let me point out on the current homework, because I've had a couple of emails about that. Let me show you a couple of interesting things that happen here. I mean, the step potential, we've already talked about that. So let's make both steps V naught so that this barrier is actually 2 V naught. Of course, we have regions 1, 2, and 3. So that's one reason to do MATLAB is you're not doing so much algebra, or you're not doing any algebra. Right? That's kind of bad for your math skills. But I can actually do stuff like this, which would just take you out. It'd take you 5 hours to do the algebra right. And I'm not going to do that. That's too much. But if a computer does it, then you can do it, and then you can figure out cool things like what I'm about to show you, which is that the transmission and reflection looks like this. So this also gives me a chance to help you if you're a little bit stuck with this. And here's energy, and if you have a 2V naught. So you're not going to really see anything happen, again, unless you're at 2V naught. That kind of makes sense, right? And what you're going to see looks like this. Now nothing happens, so it kind of looks more like the step potential in that it's kind of it's like an all or nothing. But as you can already see how I've done this differently than the step potential, that there's these resonances. And of course I'm trying to draw these on top of each other. They're supposed to be on top of each other, not doing that super well, but there you go. Okay, of course this is 1 and then 0. Okay, so what you get are wiggles. That's kind of neat. Now let me also point out that if you, so this is, I've done this for about 1 nanometer, which I said that's, go ahead and start with a nanometer. So, when you're talking about electrons, we were doing this calculation for an electron. We're using about an ED, we're using about a nanometer of a step. All that is all consistent. Okay, I told you on the homework, why don't you mess around with changing the length? Now, of course, the length is this. Change the length, and what you see is actually kind of cool. So I hope you like this. You're going to see something like this. What did I just do? I just did reflecting. So the transmission is, now I'm confused. Transmission would also be, why am I so confused? Reflect, yeah. Down to 0, so this goes. Anyway, sorry about that, I got a little confused. Anyway, look, the point is, despite my inability to draw this, I did 3.5. That's just what I did on the answer key, just for the hell of it. You get closer wiggles. Okay, now any opinion as to why? Why are there wiggles and why are they L dependent? Why was L get bigger, do they get shorter? That's kind of a little counterintuitive, don't you think? Don't you think if L gets longer, the wiggles should get longer? They actually got shorter. What do you think about that?
They feel the potential longer, so they lose a lot more kinetic energy.
Unfortunately, the model is actually so complicated, I actually can't address that.
Never mind.
I'm not really, because I tell you, I don't quite know. I know how to explain it the way I want to explain it. Tell you what region should I focus on? It's going to help to understand what's happening. Is to say where is the effect occurring? What region? Now, the transmission, of course, is the A, B, C, D, E. So the transmission, of course, is the E wave, right? So this is transmission, of course, is going to be K3. For the a lot of you sent me code. You've forgotten that in question 1. This is question 2. Question 1 points out that you need to have ratios of momentum vectors, and that's because if something goes over the hill but it has no energy, it's not moving, so it's not transmitting, right? So this makes sense, right? It makes sense that the momentum that you have to talk about transmission and reflection in terms of ratios of momentum, because again, if something just has enough energy to crest a hill, but it uses up all its energy to do so, it's stopped. And so it's not, that technically doesn't count as transmission. So anyway, that's why you would have these ratios of Ks. Okay, so I understand where the transmission is coming from. All right, but that's not it. So region 1 or 2 then, where am I getting this effect? Region 2, right? And why? It's L dependent. Yeah, and L is region 2. So it's a region 2 thing. Okay, when waves go up and down, think back to high school when you learned about how a prism works. We learned how prisms generate different color light. What was the process of waves? Waves do what to make that work? 2 words. Interference. Describe. Yeah, right. Remember, constructive, deconstructive interference. Right, so this looks like an interference pattern. So that's what's happening, and it's coming in region 2 because it's L dependent. Okay, what would be, what's constructing or deconstructing? The what? Constructing, or, well, both are happening. Constructing when it's big and destructing when it's small. But what? What's constructing, destructing? We're in region 2, so what's the answer? The waves, C and D. The C and D waves. The C and D waves are interfering with each Right, so what's happening is, if the C wave gets, if you have a C wave, it got over the first hill. Remember, the D wave is the one that backscatters off the next block. And so C and D are interfering with each other here. And sometimes they're constructive, and so that's when the transmission goes up. And let's not worry about reflection. Transmission goes up when C and D were constructing, but a little bit higher energy, they destructed, interfered, right? And so they weren't able to get over the hill because they destroyed each other. So how can you go over the hill when you've been destroyed? So that's what's happening. Now another thing is, the wiggles are proportional to 1 over M. Now why does that? That it has to make sense because that is what happened. Maybe you just don't know why, but that doesn't mean it doesn't make sense. So of course it makes sense. Why? Any idea? So it's like more sensitive the longer. I mean, it's kind of counterintuitive, right? It seems like if the step was shorter, you would have greater sensitivity and more wiggles. But actually, these wiggles are dependent on the length. The longer it is, the more these wiggles get shorter and kind of more prominent. You see them better. Why would that be? Well, it's interfering. We already established that.
That'd be like less area for it to.
Yeah, well, if the step is closer than a wavelength, then it wouldn't have the opportunity to construct or deconstruct. There's an aspect of that. One thing I want to point out is that energy is proportional to 1 over length. Right? So at this point, the way this is shown up in multiple ways. Take our waves where x is meters. The argument of an exponential cannot have units, so therefore k, if that's meters, then k has to have units of 1 over meters. Right? Because you cannot have e to a meter. That's nonsense. You can't have e to a joule. You can't have e to a kilogram meter per second. It has to be e to no units or you're talking junk. Now, we all know x is x is position, k is momentum, but notice momentum is actually got units of 1 over length. Now, of course, what you really need to get it to momentum, which is kilograms meters per second, you just need to multiply by h, the Planck constant. So that's how that translates. Okay, if momentum is related to 1 over length and momentum is related to energy, energy is related to 1 over length. So I saw a guy screw this up once at a PhD defense. It was kind of hideous. All right, but when you're doing a UV viz, now UV viz go from like 200 to 800 nanometers, right? Okay, where's low energy? Where's high energy? Right, this way is high energy. That's UV, and then that's red. That's low energy. So you know that. So I was kind of thinking that the fact that as a function of energy, I see these wiggles get shorter is probably an aspect of the relationship between energy and length. Anyway, just saying, it's kind of like embarrassing if you ever get that twisted because it comes up a lot. So this is why physicists never do what chemists do. Physicists use EV. And then the visible region is about 3 to 1.5. And your spectra look like that. It's way smarter to do it that way, but we have our conventions. Okay, now getting back to more about C and D interfering. Well, let me tell you a little bit more, because again, I have some time to kill. I want to just tell you a little bit about a language. The language that you hear very frequently, and it sounds highfalutin, sounds very like, oh, this must, the person saying this must be a Nobel Prize winner. And really they're not. It's called phase shifts. So when you see this behavior, and you're at a professional talk, people will talk about, well, you get a different phase shift behavior. Huh? Right? Yeah, what does that mean? Okay, so let me cover what that means, because it's actually not that difficult. Okay, so let's look at high transmission, right? The C wave and the D wave Yeah, really I want to draw them on top of each other. I want to draw them on top of each other, but then you couldn't see them, so I draw them slightly opposite. Okay, constructive? Yeah? Okay, now a phase shift means I simply just move, I just grab it and pull it. Right? And I think a child can understand that. Right? If I pull it here, I'll draw the C wave. Hope I draw a little bit better. Isn't that better if proud? Okay, if I shift it by pi, what does it look like? Pi is 180, right? 180 degrees. It's completely the opposite. So here's C and here's D with a pi shift. That's a pi phase shift. Phase is just the x-axis of a graph of waves. All right. Now, all right. So that's what a phase shift is. You learned that at one point. Maybe you forgot. That's why I bring it up. Okay. Now let's say that in your calculation of A, B, C, D, and IKX, IK1, IK2, yada yada yada. So there's a bunch of I's. Let's say that D picks up the letter I, right? In the calculation of the A is 1, B, C, D, and E, blah, blah, blah. Imagine that something, the D coefficient picks up a letter I at some energy. Yeah? Not too unreasonable. All right, well, let me represent this. This is also part of your next homework. You got to get used to the fact that these can be expressed as e to the I pi and all that jazz. Okay, so I, the imaginary number, is e to the I pi over 2. Put it in MATLAB. Put it in Google. Put it in Google. exp parenthesis I times pi/2, and it will spit out I, the imaginary number. Okay, now if the D wave picks up that, let's do that. E to the I pi over 2 times E. Now the D wave is a left K2 wave. All right. Now what is that? Now you should know that when you have exponentials like this, you just add them together. Now look at this. You see? So it's a minus pi over 2. Now, if I was to put that as cosine and sine, now before it was just cos K2x. Before it was just cos K2x. Now it's x K2 minus pi, and then, so that'd be minus I, sine, same thing, x. Anyway, my point being that when you talk about phase shifting, that's how it occurred. You know perfectly well at this point what solving A, B, C, D, and all that jazz means. I'm just telling you that it picks up an I, which is in the complex plane, in the representation of e to the I pi over, well, anyway, it's right here. And then you do its job, which is to multiply the IK2. What it's doing is phase shifting. That's what it does. And now again, the reason that D happens to be the letter I or whatever it is, it's a function of energy. And so in this case, if that's destructive, then you're here. And then as you move up in energy, it has some other value. Maybe it's 1, right? If it's the number 1, not the letter I, then it's going to constructively interfere with the C wave. But now you're up here. So that's what it means to phase shift. When you hear that term, oh, the wave scattered and phase shifted, just think back to this. It's actually a relatively easy thing to understand. Okay, anyways, I just wanted to tell you a little bit. Make sure that you kind of understand the language people use, because sometimes it's purposely kind of overly difficult. Okay, now, last bit, and maybe I won't have time to talk about solid state electronic structure theory, and maybe I will. See how fast we go. Let's do the finite barrier. And again, this is all about resonances. This is about scattering. Scattering, of course, means that your incoming A wave, now of course, region 1, you have an incoming A wave, and you want to see it get through this barrier. Well, the first thing it's going to do is bounce off that first barrier, and here it can, of course, if it does hop over, then you'll get a C wave. But the damnedest thing that's kind of cool is that if it penetrates this discontinuity, this sudden loss of a barrier, is itself a scattering event. Now, I have no problem understanding that the A wave bounces off this wall, but the C wave bounces off this lack of a wall. Which is like, wait, huh? It kind of doesn't make sense, especially the way I put it, but that is what's happening. Now, let me give you an optical analogy. Okay. Black absorbs light, right? No problem with that. You agree, right? Huh?
Yes.
I see a nice new black car, and I go look in the hood. What do I see? I see a reflection. Well, how am I seeing a reflection if it's black? That's what's happening. It's the same phenomenon. It's hitting the lack of a barrier, and so there's still a reflection. So weird, but not really that weird. Okay. Now what we can do is I'll do some MATLAB and show you from scratch how I do this. I'll write the code from scratch. If I fail, I'll cheat. Because I might. I don't know if I put the handout, but on the handout I actually did all the algebra to solve for E. And I told you before, we've got smooth and continuous, smooth and continuous. That gives us, it's really 4 equations. We make it look like 2, but it's 4 equations. And I've got 4 unknowns. A is 1, just make it 1. So that's B, C, D, E. And therefore the transmission is just E squared. There's no factor of, well, there is a factor of K. K1 over K1, that's just 1. And so you don't have to worry about the K's. So the transmission is E. Okay, so what you would do is smooth and continuous, 2 equations, smooth and continuous, 2 equations, divide them, makes it a little bit easier, and solve for E. There's a matrix way of doing it that makes the solution a little bit easier. In the handout, and I think I have that on the website, I actually just sat down on pen and paper. I mean, I did it with Word equation editor, but I actually solved for it basically by hand. It's like 4 pages of algebra. That's why I'm not interested in having you do this, but I did do it. And so you can look at that if you want. Now, unfortunately, the results depend on whether energy is less than V or greater than V. That's because you're going to pick up, you're either going to be C e to the minus x, d e to the plus x, or it's going to be imaginary. So anyway, you've seen enough of that. Hopefully that doesn't blow your head off. Anyway, so we have what is ultimately a pretty hideous equation. Is the solution. And what really makes me want to vomit is that minus 1. So it's the inverse of that. So that's great. Now, one thing that's kind of interesting is if the barrier is very long, so Ka goes to infinity. I'm sorry. It goes to infinity. You can make an approximation to this. You can say sinh goes to percentage x goes to like 1/2 e to the x. Sorry, John. So anyway, and so this turns into, if you ever read up about this, this is the part that people are fascinated with, and that's why I'm mentioning it. So, so the point is that, so this is what you often see, E over V. V being the step, which I usually use V naught, but sorry, should have put a little V naught there. The point of this is that you can always tunnel through a barrier. So remember, classically, a particle doesn't have the energy, it won't go through, but quantum mechanics says there's always a potential to go through. It's just a probability, not potential. There's always a probability to go through, and that's it. And it's exponentially decaying based on how far the barrier, how long the barrier is. Oh, sorry, A is L. Oh, my bad. I'm mixing two different languages here. Oh, my bad. I got my notes on Wikipedia. Sorry about that. And it would help if I, oh God, I'm a mess. I thought I started out okay, but now I'm a mess. Let's see here. You can also, anyway. So again, whenever you read about this, you almost always run into this, so I just want to show that to you. And it's just an approximation to the real equation, because the real equation is a nightmare, which you can see in my handout, or of course, as you are doing on MATLAB, you're going to solve for that yourself. MATLAB doesn't make it so nice looking. It is going to make this, you remember since, you had it on your last homework, e to the x plus e to the minus ix over e to the x minus e to the minus x. Anyway, MATLAB spells it out because it doesn't quite so automatically recognize sinh. Then of course if energy is greater than V, which is, this is actually the kind of more interesting one. The transmission, let's see, hopefully if I won't screw this up, this point. So it's kind of traditional to use the letter A for representing distance, but I like to use L because it's just English language. It just automatically means length. Most people will see the letter L and just assume it means length. And there's that +1 I forgot last time. So the sinh becomes sine. That's really all it is. And in terms of the transmission, which, again, you should basically see this behavior if you're doing it right. There you go. Of course, the potential is about there, energy. I mentioned that the transmission is 100% at certain spots, at certain resonances. But when you look at this, you need this to be what? For the transmission to be what? There's a 1, so this is 0. So you need this to be 0, which you need sine to be 0. Right, and you can do that. When K to L is equal to n pi. Now you may recognize this, and this is basically particle in the box. Right? So I won't solve it because there's a potential in there. It's a little bit more difficult. But what you find is that if you plot the wave functions, maybe I'll do that. You see behavior like this. they look like this. There's one. There's another that looks like this. Sorry, I didn't get myself in another room. Here's another one. That one also transmits fully. And then the next one that transmits fully. And again, keeping floating wave functions. Like that. And all the wavelengths in between, not so much, they don't transmit fully. But you can see, it's not perfect because it's a more complicated model, but you can see basically that particle in a box behavior. It's really right in the middle. I've got to get a perfect of the world away. There we go. That's a little bit better. So anyway, right in the middle of the way. I didn't feel like that very well. Okay. So anyway, there's that. So why don't I see? Let me turn on the projector here. Let's do a little MATLAB. In case you're, especially if you're a little stuck. Oh really? Cool. Got it. Okay, this is going to warm up. One of the things that people use this for is, here we go. Okay, we got this going. People use these models to describe nuclear decay. So when a nucleus breaks up, it does so by emitting a beta particle, which is I think that's 2 protons, 2 neutrons, so it's a helium plus 2. And what happens is that the trap that it's stuck in is the strong nuclear force. And if it can get out of the purview of the strong nuclear force, what happens is then the nucleus is positive and the particle is positive, then they just shoot away from each other. So there's this trap that it has to tunnel through. It has to tunnel through the strong nuclear force, and if it gets away, it's just going to blast off to infinity because you have 2 positive charges right next to each other. Anyway, that's just one of the main things that people use. This tunneling stuff for. Okay. Anyway, so let's do one of the problems just to make sure you're up to speed. Okay, there's kittens. That one's mine. All right, so let me show you one of the things that's important about this is how do you solve it? When you don't know what to do, what do you do? Okay, I Googled systems of equations MATLAB. That's the first thing I do. I have a problem and I want to use MATLAB because I'm very comfortable with MATLAB. I know that all of this stuff, this ABCD, is a system of equations. That's the word for it. So I just Google system of equations MATLAB. I clicked on the first site. Okay, first site, how do I do this? So now you're going to see, this is how I figure out everything. I'm just going to look at this and just steal it. It's right there. There's the MATLAB code. All I'm going to do is steal it for my own purposes. Just have to do a little translation, right? So let's write a script. And you want to do a script, of course, because if you screw up, I always clear all, because usually I'm doing a bunch of things. So I can see from that website, the first thing you tell it are sims, X, Y, Z, but my sims, of course, are going to be B, C, D, and E. Now I am going to have a K1 and a K2, and then I have a box length. Okay, and it says semicolon. Again, oh, it doesn't have semicolon. And honestly, it doesn't matter, but let's just steal it word for word. Okay, then equation 1, equation 2, where there's a double equation in the definition of the equation. So the first boundary condition is for at x equals 0. So the a is 1, b is multiplied by e to the minus I kx, where x is 0. So that's just b. So anyway, hopefully this is familiar to you. Now I have a semicolon. And again, hopefully I won't. And I just keep writing and I keep writing, and I'll have 4 of these. No reason. Now you could divide them. You could divide the wave function divided by the derivative. You could do that or not. It doesn't matter. It's fine. So now if I recall, equation 2 is the derivative. So that's ik1. Now I usually like to make sure that MATLAB knows what I is. You might accidentally screw it up. And then C is I times K2. Okay, and again, that's at x equals 0. Sorry, I'm doing the step potential. There's a, I got C plus D here, don't I? Yeah, did I get this right?
That's got an I. Difference.
Huh?
The eyes cancel out, shouldn't they?
What?
Shouldn't the eyes cancel out?
They can't really, but MATLAB will figure that out. So I usually choose to leave them just because of my own notes. I don't want to get confused about my own notes. But you can do that if you want. It's just that if you're following your own notes, you might confuse yourself. It's just an extra step. And if you don't really need to do it, I would suggest not. I1. That's a positive, right? Yeah. Okay, this is the derivative. And, K2 times C. Minus I. My finger slips with that right there every time. Okay, then I times K1. Okay, hopefully I did that right. Now what I do is I go back here. Okay, I see. You know what I'm going to do? I'm going to be real cheap. I'm going to cut and paste. Okay, that's easier. Now I can see where the equations go. So this equation is the matrix. I mean, I am a native English speaker, so I know what those words mean by themselves. But as it applies here, I don't, what does it mean for real in terms of mathematics? I don't really know. Okay, now here's something I saw some of you make a mistake with. All right, you have 4 equations and 4 unknowns, right? Right? No, you have 8 unknowns. A, B, C, D, that's a B, C, D, E, that's 4, 5, 6, sorry, 7. You have 7 unknowns. You have the capacity to solve for 4, but you actually have 7. So you have to get this right. You have to tell it that you are looking for B, C, D, and E. Now what that means is it then understands to solve for B, C, D, and E in terms of K1, K2, and L. Otherwise it wouldn't know. Maybe you're trying to solve for A, B, C. Maybe you're trying to solve for A in terms of B. That doesn't make sense, right? That's the purpose is not to do that. Okay, so, and then I see this command here. So I'm just going to copy it. You may notice that this is where your code comes from. Okay, see, we're almost running out of time. So now I just control A. I love control A. Control C, control V. And depending on how fast this computer is, I'm assuming I made a typo somewhere. I mean, there's no way It's a miracle I got it right. Look at that, I got it right. Okay, now the thing that sucks is I'm going to copy that. Let's see how, oops, what was that? Well, I don't have time, but let's say if I wrote the code, what I would say, I have the conjugate. This is how I do this, because otherwise it's like really difficult with this command so long. So conjugate this, Control V, and then I come back, and then go back in here, Control V again. Then I go to the end of it. Again, this is, I'm just being practical here, that when you cut and paste these long lines, it's a real nightmare. There you go. So all you need to do is define H, M, L, then when you're here, energy is equal to K1 is equal to K2 is equal to, and then there you go. That's all there is to it. And again, I've given you plenty of example code. You've already done the step potential. So in lieu of having a review session, I hope that this does it. I wish I had time to actually flesh it out, but I think that other classes are coming. You're all okay. You can do this now. Okay, when it comes to the double step, you're just going to have 8 equations, and it will end with you have EF, GH, EF, GH, I. So it'll be the letter I squared is your transmission. This is going to work fine, but what's going to kill you is when you type an 8 instead of a star. When you forget the letter I or an L. There's like 50 of these, and not one of them can be wrong. Now that's, trust me, you've got an hour or two of finding that letter I that's missing. It's not going to work. It's going to drive you crazy. But when it does work, it does. And this is why physical chemists make more money than